We're going to take some time with the diagrams to help you identify what you're looking at and explain some of the terminology. Now, when we see the electronic throttle control module, like you see highlighted here at the top of this diagram, when it's connected directly to the PCM has dual processors. It's going to handle the self-checking along with all the other main processing, and it's all built into PCM. Where it becomes confusion is when we have a separate module. When we have a separate module, some of the calculations for electronic throttle are handled by the module, but a majority of them are handled by the PCM. So we'll talk about that because that does affect our diagnostics a little bit. Now, whichever one we're talking about, the main processor, which in most cases, in fact in all cases, is the PCM. It performs all PCM or ECT management tasks. It makes a decision of what throttle opening to have. Either if it's a direct, it directs the motor to change it, or it sends information to the external module to change motor position. The checking processor performs redundant checking of sensors of the electronic throttle control system. It does the diagnostics for it, and the redundant security moduling, and the fuel and spark output enable. Well, that's an important thing. Let's start and talk about fuel and spark output enable. If the PCM determines that we're out of control and we are not able to control engine speed properly, it will disable fuel and spark, shut the engine down. Its first reaction will be to pull the throttle to an idle. If that doesn't seem to be affecting the change it thinks is needed, it will take the drastic step of shutting fuel and spark output down. All of this is done self-checking. So all of this information is being done by a checking process. Electronic throttle controller integrity is assured through several levels of diagnostics. Let's talk about these levels of diagnostics. Redundant computation of all critical values. Just like analog brakes, electronic throttle control uses two processors to examine all the critical inputs, make all the calculations, and see if it comes to the same throttle. This is done by two different processors. Rationality diagnostics. Is this reasonable? Does the power modeling look like what we'd expect to see for engine power? If it doesn't, it's going to go into reduced power mode because it can't determine what's wrong. We're going to talk more about that later in the diagnostics. And when equipped with the throttle control module, this is going to interface with all of the components, the accelerator pedal, the motor, and the throttle position sensors, and do a small portion of the processing. Some of the self-checking is done in ETCS. But the control of the motor is done by the external control module, but under the direction of the PCM. The majority of the processing is performed by the PCM. Now, this was done to make a standalone system that provided a low-cost solution for vehicles not designed with ETC. The majority of the processing is performed by the PCM. The external module just handles the extra signals. When there's a separate processor, the PCM and that processor are going to communicate over a data network. Now, we have a complete training class on network communications. We're going to highlight 3 or 4 of the systems here and show you the lab scope patterns. But to really do a proper job, go to our communication section and go through all the diagnostics and how to set up the scope for these patterns. Now, the engine will not respond to changes in accelerator pedal position if communications is lost with the external module. So this is important. This is our first failure analysis point. If you move the throttle and nothing happens, you might want to make sure you have communications. And go to communications. We'll talk all about how to do that. But let's look at the protocols going to be used. Chrysler uses PCI. PCI is not connected to scan data on this Chrysler. It's a single wire protocol that communicates at 10.4 kilowatt per second, and the signal goes from 0 to 7.5 volts. The point we're making with a lab scope is there's a number of critical things we need to see here. We'll show you how to set it up, your lab scope, why it's set up the way it is. If you'll go to our communication section and look at PCI on the communications in the PCI DSO patterns under that title. The reason we're bringing this out is you can have scan data working perfectly normal, and this PCI bus can be giving a problem unless you go in specifically with a manufacturer specific software enhanced scan tool. You're not going to be able to check to see if this signal is present. This is going to have to be done with a specific scan tool set up for Chrysler. Now you can buy an aftermarket that has enhanced software. It will do this job for you. You need to do a status report and see who can communicate. They also use CCD, which is an older protocol, but it's used all the way up to some late model trucks. It's a 2-wire. It's a very special setup. It's 284 millivolt signal. If you don't know how to set your scope up, you have to definitely go to communications and look this up. It would take us too long to explain it here. Or you can look at the quality of that signal. GM Class 2. This software, or this class, does use scan data. This is the same protocol they use for scan data. So you'll be able to see scan data here. You could not on the Chrysler. It was a separate program. It's a single wire protocol that operates at 10.4 kilowatt. Signal goes between 7.5 volts. And again, go to the communication section. But if you cannot communicate with your computer, in all likelihood, the computer cannot communicate with the external module either. You're going to have to go find out why the system is shut down. In that case, you're going to have to go diagnose this. Ford uses Standard Corporate Protocol, SCP. It's a 2-wire protocol. Operates at 41.6 kilobits. The signal is plus 4.3 to minus 4.0 volts. It is the same protocol used for scan data. If you cannot communicate with your scan data, the odds are this communication is shut down as well. And then Asian and Euro imports use UART. UART is an acronym for Universal Asynchronous Receive and Transmit. It's also called the LIN module, Local Information Network. You'll find UART is the predominant system other than the data used to get scan data communications. UART is not used for scan data communications on imports or Asian. It is going to be used quite extensively for module-to-module communications. And there's a specific way to set this up as well. This signal, as you can see, looks very much like the GM Class 2 and the Chrysler PCI, except the voltage levels are different. Go to the communication section to get a good view of that. You can have scan data operating, and this bus can still be inoperative. To see this data and get status, you must have an enhanced scan tool. And this is the newest of them, CAN. In this case, it will be using a high-speed network. It's a signal at the bottom. It operates at 500 kilobits per second, really fast. High-speed CAN varies between 1.5 and 3.5 volts, with the 0 point at 2.5 in the middle. This is what you're going to be seeing more and more of, used very extensively. And again, go to the communications to really get a view of this. Remember, any of these systems shut down. This system is used for scan data communications. So that's the good news. Here's what a system looks like that's going to be using Class 2 information. Now what we're trying to show you here is there's a lot of modules. Starting at the left, got 1, 2, 3, 4, 5, 6, 7, 8, 12, 13, 14, 15, 16, 17, 18. The 18th module is the one we're interested in this particular case. Let's magnify that. That's the TAC module, or GM. It's got two wires. Now, that's not the only two wires going to that module. That's the two wires carrying communications to that module. It has two wires for communications, redundant communication lines. It doesn't need but one, but it has two because of redundant systems. Here it is on the actual vehicle, on the fender well over here. And there's the signal we'll be using. Now, there's some very specific procedures for verifying that that signal is the same signal that's on the bus. What we do, if we think we've got an opening, and we got a status that says we cannot communicate with a particular module, what's the status? That's when we take our scan tool, we try to communicate. Some software calls it pinging. We see if we can communicate with a TAC module. If we cannot communicate, now we're going to have to diagnose a communications failure. Question is, we can't communicate with anybody. Anybody on this bus can shut things down. All of these modules, they go bad, can pull the module low, can talk all the time, hold it high. Any of those things can cause a malfunction. If we have signals here, we got to make sure that the signal here is the same as the signal on the bus. Why is that? Because the signal on the bus is communications for all of them. If we see a signal here that is not identical to the signal on the bus, we use a dual trace scope, compare them. That's telling us that the TAC module may be trying to communicate out, but since it's not the same signal as the signal that's present on the bus, it's not making contact. We've got an open circuit. Remember, we've got two wires here to help alleviate that problem. Redundant signals, as we talked about before. But any one of these modules can shut this down. So if you have any problem here, you think you've got something that needs to be worked on, go to the communications program and study that.
We're going to have multiple sensor inputs. Now, not only are they going to be multiple, they're going to be divided. We're going to have accelerator pedal sensors. They're going to be the motorist request for speed changes. Throttle position sensors are going to be mounted where they've always been mounted, out on the throttle shaft at the throttle bore. And brake switches. We've got to make sure we're doing what the motorist or driver intended to do. Let's talk about these accelerator pedal position sensors. They're position sensors that are inputs to EPS. Remember, this is the only input we have for increasing speed, is the accelerator pedal position. They signal the driver's request for a change in speed response, hold speed, decrease speed, increase speed. What's needed? And they are potentiometers that measure accelerator pedal movement. Now, we all know about potentiometers. They're a device for measuring electromotive force or voltage by comparing with a known voltage reference. It's a nice theory. How does it really work? As we look at these housings, we'll take a look at some of the ways they are built. We find that some of them have a totally external sensor, like this one here. Let's talk about how and what's inside this sensor. Now, the way this sensor works is like all sensors we've had. Most of them use a 5 volts for a reference voltage, and most of them use ground as a zero return. And they all have a signal that varies depending on where the wiper is. Now, we find that some start low, like the wiper here at the bottom, and sweep around to the high side, while others start high, like the wiper here, and sweeps around to the low side. Either side will work for the computer because it's going to be looking at the data. Now, what we know is very few of these sensors actually cover the entire operating range. We find typical ranges of 0.5 to 4.9 as the maximum range possible on a particular sensor. That's so that if we get 0 or 5 volts, we know something's gone wrong. But the voltage is usually limited and doesn't cover the full range. Now, some of the early systems went to the extreme of actually having a cable go through a tube and pull on a spring to give feel. Now, this is kind of taking it a far piece, but they want to make sure that the customer had the same feel for the accelerator they've always had. And it's shown with the external spring here. Looking on an actual vehicle, you can see the spring there. Some of the newer vehicles have gone to internal springs. But the springs aren't what really interests us. It's the electronics here inside that really we need to focus on. If we look inside this particular one, we have two sensors, APP1 and APP2. They both have a 5-volt reference, they both have a ground, and they both have a signal. Let's talk about that. When we were going to worry about how the sensor's operating, we verify it has good reference voltage. We verify it has a good ground return. Then we judge the signal. We know when if it was one of those that could go to the maximum at the top, which would be rare, it would read 5 volts when it's at the very top, nearest the 5-volt side. And if it were a linear potentiometer, right in the middle, it would read 2.5 volts. And if it could go all the way to ground, it would read 0. Now we know that no sensors do this. They don't go between 0 and 5 volts. They have a limited range. But the amount of resistance determines the rate of change, how fast the voltage changes for each degree of movement. When we take a look at this, we begin to understand what we're talking about. We've got 3 different pedal positions. Pedal 1, pedal 2, and pedal 3. As you look at this chart, some start high and go low, some start low and go high, and 1, 3 starts kind of in the middle high and ends in the middle low. Doesn't cover the full range. What the PCM is going to be doing is calculating throttle position off of all 3 of these and seeing if they agree. How does it do that? Well, let's look at it in the scan tool. Here's another one where 1 goes all the way up linear, 1 goes up partway and stops. Remember, the amount of resistance is going to determine the voltage rise by the degrees of movement. So you'll get some that go to 4.8, others go to 3.8, 3.1. That's the max range on both of them. We're looking at this with a scan tool, but we know sometimes we're going to have to use a lab scope. Now we've set this up to read 2 milliseconds per division, which gives us a full screen of 20 volts. 2 seconds per division. Each one of those rectangles on the screen is 2 seconds wide. There's 10 of them. That gives us 20 seconds. We're trying to keep our promise to you of telling you why we set this up. We set this up so we have time to sweep up, sweep down, and catch it on the screen as a one-man operation. We're checking to a signal that's not going above 5 volts, so we're going to use a 5-volt scale. Then we're going to sweep test, sweep our signal up, sweep it down, and look at 2 channels. The blue channel is on one sensor, and the red channel is on the other. The blue channel goes up to 2.3 volts, and the red channel goes up to 4.4 volts. But look, we want to make sure they both go up together, stay high together, and come down together with no extra blips and not have any periods of severe disagreement. We're going to talk more about that later when we get into some very in-depth diagnostics. But the computer is going to use both those signals. It's going to say, oh, the one that starts low and goes high, when it's at 1.2 volts, that's 9% throttle. And when it's at 4.77, that's 98% throttle. Okay, it can do these by calculating each one individually. This chart would obviously be similar for both of them, but the voltage scales would be different. But remember, the PCM is going to use those voltages to calculate throttle opening and then compare the throttle opening. Is the pedal position the same? Is the throttle opening the same? If they come out the same, the 2 are doing the same thing. It's going to be doing a constant comparison. Is the signal a valid request? Is the signal accepted? Is it in the range? We saw one on our example, 0.5 to 4.8 volts was the range. Is the signal credible? Do all the sensors agree on the angle of the throttle pedal, accelerator pedal? Not voltage. Do they agree in the accelerator pedal position in degrees? Then we're going to be looking to answer these questions. The 2 processors are going to do this, both make the same calculations and compare them. Then they're going to look at rationality diagnostics, and power modeling is used to detect problems that would affect engine power. What it's saying is, if we look at engine control signals and the throttle position signals, do they seem to be valid? Are we requesting what is the operating conditions say should be requested? So we're constantly trying to answer these questions, and they're going to be important to our diagnostics. To accomplish this credibility check and this redundancy checking, it's going to be based off all the inputs we know are going to be used on any particular vehicle. What are we supposed to be doing? What's the engine performance doing? What's our power demands? What's the motorist intent? These are all the basic fuel control inputs we expect to see. Now, battery voltage is something we don't think of as being critical, but remember, we're moving the throttle with voltage now, not a cable. So it becomes a critical input. When battery voltage goes too low, the processor will place the ETC into a fault mode. Now you think, oh, that's so simple. Well, yes, it is simple. But remember this. It could be that this system is doing strange things because one of the processor has a problem reading battery voltage, loose connection, bad terminal. We've seen some outlandish things putting these systems into a default limited performance mode. Now, when wheel speed, vehicle speed, and brake input, the computer must always be informed of the motorist or driver's intention to brake or stop the vehicle. This will override the accelerator pedal position inputs. If we think that the accelerator pedal is open or the throttle opening is too wide with the brake switch applied, we're going to get really worried. If the brake switch and throttle opening are in disagreement, the PCM is going to determine it is unable to close the throttle. It'll shut the engine down. We talked early on and gave you those theory things about the system having spark and fuel enable. Well, the reason it has spark and fuel enable is if it thinks it has lost control, it will pull those two enables, shut the system down. Now, this is the last resort. We're going to talk about it more later. But what you need to understand is every time this system thinks something's wrong, it's going to take some action. Not as drastically as this necessarily. Let's look at some other things and what might be happening and how we have to diagnose it. Back to our original drawing. We gave you earlier two sensors, and we showed you the theoretical thing. The first and foremost thing is to check for trouble codes. Diagnostic trouble codes can help us greatly. We're going to use a P1125 Accelerator position sensors from two of the three signals sensors don't agree. Let's break this down. Here's the enabling conditions. The sensors disagree for 1 second. Now, in throttle positioning, 1 second is an eternity. And we'll talk about that later. And there's things this can block. We'll get back to that. Here is an actual scope pattern we came up with. Now, as we promised you, we can always keep going back to the same thing. We're still at 2 milliseconds per division. We're still on a 5-volt scale. Now, we put superimposed on here that this sensor disagrees for 1 second. Well, 1 second is really long here. In fact, the throttle is open completely for about 1 second, a little over. Each one of these squares, which we've darkened up here, is 2 seconds wide. So for this to be setting a code, it's going to have to be 1/2 the width of one of these rectangles you see. This glitch, which is real, is not 1 second wide. If it's not 1 second wide, it's not going to set a code. But look at the blue trace. Now I want you to look at some stuff. Look at the distance between the red and the blue trace as we open the throttle. They are not perfect. We're not looking for absolute perfect mirror images. They get varying distances from each other. But what we can't tolerate is this glitch you see. And actually, we see two of them. One before we open them and one almost open. This causes a major drivability problem. Why? Because the software says, wait a minute, I do not have agreement with the two signals. So it does its plausibility check. But which one of these signals looks plausible? Well, my engine speed has been doing this, and therefore I am going to believe the blue trace and ignore the red trace. All of that takes time, and when the computer is making that decision, it goes to limited power, makes a decision, and continues forward. This is one of our common complaints. The system makes a reaction and then goes back to normal. So this is something you might be seeing in reality. This is a failure we identified that could not be identified by other shops. In fact, the new car dealer told the customer there's nothing wrong with this vehicle. There's no codes, there's nothing wrong. So don't assume it's going to be wrong. Now, we're getting back to our code. If we have codes, it can block some other things. We bring up blocking conditions constantly because people frequently ignore them. Whenever you work on anything that can block monitors, make sure you look at the mode 6 for things like fuel control, catalyst monitor, misfire canister, and EGR, because you may have problems there that have not been counting failures. Testing, there's a lot of different testing. Here's telling you what the position sensors should be. That's all well and fine. But we find that you can measure them with a voltmeter, scan data you see in the background, and a lab scope. Readings on a voltmeter are going to vary by what you have. We have 3 different configurations. Both signals move in the same direction. You just saw examples like that. The 2 signals move in opposite direction. You'll see examples of that. And each has a different peak voltage, and you'll see examples of that. Look at these 2. They're going along together in the DSO. They're both going up, they're both coming down together, and we've offset them just slightly so that one's not sitting directly on top of the other. That is a normal pulse. That's normal we expect to see. You're looking at the same data on the scan tool, going up to 4.8 volts, and they both go up to 4.8. Now, the scan tool is showing us this same information, but it doesn't show it as fast. Look, here's an example. Here's the scan tool versus the DSO. When we opened the voltage, the throttles, on a scan data, it went straight up, just like it shows it going straight up in the lab scope. But when we got our glitch, the glitch did not show up in scan data. It was too fast. No, scan data is massaged. The computer has decided that wasn't valid data. How do we test for it? Well, we start off, go back and see if you have 5 volts. We're looking at 5 volts here on our DVOM. Works perfectly fine. Here's a situation where the signal should go to 4.4. We raised it up, it only went to 366. You could find that with a voltmeter, you could find it with a lab scope, you could find it with scan data. Doesn't matter. If the voltage isn't going above the reference voltage, or to the reference voltage, like in this example, it was a result in reference voltage being low. Be aware that if it doesn't get 5 volts, it can't show you 5 volts. Good ground, 0.05 volts. That looks good to some people, but that's our max specification. We would never want to see it any higher than that. Here's one that's 760 millivolts. That's the lowest it can get. Now the question is, we can't get below 760 millivolts. Is that a ground problem? In this particular case, it was a ground problem. A bad ground circuit kept this so the minimum voltage we could get to was 760 millivolts. And here we go and measure our voltage. Here is a signal voltage, 0.67 volts. Is that normal? Could be. Depends on what the specification. Try to find a manufacturer specific specification for normal signal, foot off the pedal. Is a signal here on our scan tool. We go up, they both look like they go up together. Our throttle and our accelerator pedal follow the same path. Okay, remember the accelerator pedal is the driver's input. The throttle is the result of the computer deciding that input is valid and moving the throttle pedal. So that is going to be one of the things you'll be seeing as you look at scan data. You'll look and it's a decision that has been made to move the throttle. Just keep stressing that factor. We're going to be using our lab scope. Now what we've done here, slightly different, and we keep telling you we're going to change things. We have changed this to 1 second per division because we're working a little faster and we're doing it as a two-man job. And we're just looking at changes. And we're going to be watching for any changes where these two don't agree. So here's another sweep test. We're back to our 2 seconds as a one-man job. Now what I want to talk to you about here is if you look for the spacing between these, it's varying very slightly. Sometimes they get close together. They're not perfectly smooth lines staying equidistant all the time. That's because as they move, there's minor imperfections in the potentiometer. And don't worry about minor changes like this. Both of these go up and come down at a proper level. Now if you'll notice, we've offset them just a little bit, and that's to make it so we can view them easier. Here is one we've got to really spend time talking about. Now this was a problem we located only with a lab scope. There were no codes. The car had a momentary lag in power, then picked up again afterwards on an acceleration. And it comes in at different points at different times. What happened here is as the dual processors computed the two values, at the one point we had the big glitch. The red and the blue did not agree. When they didn't agree, the processor had to stop and say, which one is valid? We think the blue is valid, took the blue and continued on. So it was not enough to cause the system to go into a shutdown, but it was enough to cause the system to stop and recalculate. We're hearing this as a frequent complaint from motorists. The vehicle did something, did not like the way it performed, but it cleared up and proceeded on in a normal manner. That's the standard program we're hearing about. People saying, hey, it was there for a moment, then it was gone. So this is an important way to find problems that do not set a code. Let me say it one more time. This is the way we find problems that do not set codes. Why? Because it may take whatever. One code said it took 1 second. 1/2 of a second is 1/2 division on 2 milliseconds per division. This is definitely not fast enough for that. This is the worst ever TPS. It had a dropout in the middle. It had all kind of erratic noise. It failed emissions miserably. It had low power, would not accelerate. Why is that? Because as you tried to accelerate and you got the wide open throttle, it went back to idle. It totally confused the PCM. Wonders how long would it take before somebody spotted this? Had to be going bad long before it got this bad. But this is the kind of information we can see on potentiometers. It's rare. Now here is one in scan data that shows a problem. And, by George, good news for you, it set a code. Why did it set a code? Well, the first clue is we're looking at a scan tool. That means it lasted a long time. Notice as we're going up in acceleration, APP1 drops off while APP2 is going up and continues up. So the first, they go together, go together, go together. When you analyze grafting, Look at a point in time and see what is happening at that point in time. Look at the history. They followed perfectly until they got to a particular point where APP1 dropped off. It set a code, you change it. This is where you don't need a scope. So, different levels. You can do it with a lab scope and find no codes. You can do it with scan data and find code problems. That's a big division. When you see this big step change without the throttle moving. Now, rationale. If these two signals have been agreeing all along, is it rational for APP1 to drop off when APP2 shows little or no movement? No, it is not rational. What happens is we had a slight increase in position for APP2, and that slight increase in position resulted in a drop in voltage for APP1. It's a dropout like we just saw in the world's worst sensor. So this is an example of what you're going to find with a scan tool. When they don't agree, they agree all along here. Every time we do something, there's pretty much agreement. Here, we can see it real time, high speed, and we can avoid having to worry about missing a dropout. So this is why we use this. Again, we're back at our 2 milliseconds per division, 5 volts. I think we beat up on why that's doing it. Now, there are linear 3-wire Hall effect sensors. They're used in dirty environments, usually heavy-duty trucks, and the output tracks the changes in magnetic flux density depending on the magnetic pole being affected by the voltage increase or decreases.